All right, just a quick review of what we did on Monday. We talked about testing code, where you want to write a little bit, test a little bit. Write a little, test a little. Reminds me of a song, but I won't sing it for you. Piece of test code here, where we generate our own little array, unsorted. We're going to be making bigger arrays than that, because a array of 10. What good is that for testing how long it takes? You have a short array, just the time around creating the array, the overhead is part of your measurement. You want to be measuring the sorting part of it, not just the code that creates the array. Here is then the call to the sort. In this particular case, the sorting algorithm is going to take two parameters, the list and the length of the list. Because the author doesn't like to keep creating lists, we keep a separate variable of how many elements in the actual list are being used. I've found with the selection sort or the insertion sort that we only reference it once in a loop, so I don't even need to send it as a parameter. But that's a variation on the selection sort. And then we list the elements in the array. And on Monday I mentioned that it's helpful to list what's in the array before you start, just so when you're generating output, you see the before and after that your algorithm is actually working. So this is showing that it's working part of the code. This is not doing any testing of times. That would be capturing the system time. So there's our test data. There's the running of the code. And there is displaying results. Any code you write, you need to develop a testing for it. Sometimes it's the whole program running that is your test. Other times, if it's a bigger program, you will actually write a separate program to test the piece of the larger program. And you can spend just as much time writing test procedures as writing the actual code itself. You may actually spend more time writing test procedures to test this code that is critical to the running of a bigger system. Yeah?
Data validation, is that considered a test?
Yeah, in some ways. Yeah, that's part of the user interface typically, or part of the gathering of data. Before you run it, before you feed it to your system, make sure it's valid data. But depending on your system, if your system is constantly collecting data, it's constantly having to validate data as part of its operation. If you're expecting to fed it good data, filtering at the start might be something you expect a separate program to be doing. But still, you want to test your program. In case that program fails in validating properly, you want to not crash if you suddenly get fed bad data. You would produce an error message like, wait a minute, data is invalid, I can't do my thing. So send an error back to the culling program.
Even if I'm using more memory space, more processing power, that doesn't matter. Just keep adding function and kind of testing.
Well, and usually the testing is separate from the final product. You ship your program with the testing code removed or disabled, and then only enable it when you're troubleshooting. And oftentimes, you'll find this in many programs that you can run in a debug mode or in what they call verbose mode. It'll suddenly be doing all the testing. But normally you want it to run efficiently. But sometimes as part of the program, you need to validate input. So that would be like a portion of the code that's constantly running. Most of the time, though, you're writing code. Back in the lab, you do lots more testing. And then when it's running, you're doing validation, but not as much heavy-duty testing and timing. So here's the example code in our GUI, where this one we did a bunch of system out print lines. The only difference here is now instead of system out print lines in our program, we're appending information to a text area that's in the program that I gave you in Chapter 14 exercise. And if you open up the Chapter 14 exercise, I have given you the code for the insertion sort. So for you to add comments to as we look at this insertion sort. So there's the test data. There's my running the code. And the show results is the only part that's different here, because instead of doing a system out print line, I'm appending the output to a text area. This is what we covered Monday. Now, the part about testing how fast code goes, that's another critical test. You want to know how efficient your code is. That it works first, that's super important. That's highest priority. Second is, okay, it's a graphics program, and I'm shooting the gun at that character. I want to see that the little bullet travels in the right direction, and the graphics don't glitch because it's running so slow. I need to make it efficient. And a quick, easy way to test the time is to gather the clock. Now, it has to be a very accurate clock. We don't just take the time of the date and time clock. That would be seconds. Most things happen much less than a second on our program. So we need to get nanoseconds. They call it nanotime. Oh, and I have a typo there. It's capital S. It's system.nanotime gives us a very accurate clock. I found out with that as I was doing a little searching. I used to use time millisecond, but then I came across someone that said, no, you shouldn't use that. Nanotime is better to use. And this was on Stack Overflow. And I thought, his reasoning seemed okay. So I decided to recommend using, and I'll be trying to use nanotime. Multiple ways to store time, but in Java, a nice accurate clock. And then, of course, when I run it, first of all, I get the time before I run my code, and then I run the code with the extra E, and then I capture the clock again, and the time it took me to run that algorithm was the time end minus time start. So we're measuring that as part of testing. All right, now a little philosophy here. What do you think the hardest thing about programming is? Debugging, capturing, reading other people's code, fixing that problem. You got that red squiggle somewhere, and you can start randomly entering code, or you have to think through and review what did I do wrong. So, yeah, that can be very hard. I suggest even a harder thing beyond that is someone gives you a problem, and there is no definition of how you're to solve the problem. In class, we give you, okay, here's how we want to approach the problem. You're not going to have a teacher in front of you saying, oh, here's how it's been done. You're going to be writing code that maybe hasn't been written before, and you've got to come up with some new code. You've got to think through that problem. Like new features, a harder problem to solve, like sorting lists. And by sorting a list, you're helping a harder problem, such as searching, to be done. You're doing some harder data analysis that no one has done before. This is huge on the web today. Processing tweets and chats and postings to social media, you can find out about what we should be marketing to that person based on what they have been posting, based on the websites that they've been visiting. There is huge dollars for companies to send to you email knowing that you've been searching for car parts for your Chevy, and suddenly they know you're in the market. You're ready to either buy a Chevy, you're ready to buy parts. They'll offer you all sorts of other things. And there's some crazy analysis that's been done to actually find that based on certain pieces of information you wouldn't think are connected at all, they know that in June you're going to buy a Volkswagen. And they should be sending you an email about that Volkswagen in June, because based on their studies, people that do certain things, they bought a piece of gum at Walmart on Tuesday, January 1st, and they watched the movie on March at some theater, they know you're more likely to buy this product. Crazy data analysis. That is huge. So if you get into databases, learn that kind of stuff, you could make big money, even for a company. Going into a company, analyzing their data, finding that you can improve efficiency by 1%. If they're making $1 million a year, which is not a big company, that 1% is a lot of money, and you can get half of it, or maybe 1% for that year, and then go on and help another company. I know a guy that did that. He was a parent of a student at Emmaus, and we're talking. He does that for a living. But once a month, he'll visit a company, improve their efficiency by doing the data analysis, get paid, and then he'll spend the rest of the month traveling the world, tasting exotic foods in the mountains of Switzerland. It's a crazy life. But he was happy because he could do this data analysis. Maybe you can live that dream someday. So you have a problem that you have to solve, and you don't have to solve it in a vacuum. Although if it's a really exotic problem no one else has done before, it's going to be harder to solve. Most of the time, similar problems have been done, and so discussing with colleagues, researching on the internet, looking at your past work, you'll probably have similar problems you solve. That's a great way to solve problems. Visualize the solution. Draw pictures. I always draw pictures thinking through the problem I'm going to solve. And look at similar solutions. Then you write your code. Then you test to verify that it does solve the problem. Okay? So, the topic today is the insertion sort. First thing to do is visualize someone's proposed solution to sorting data. And this came from Wikipedia, where you look at the first number and just go down the row comparing that first number to something else, putting the next thing in the right place. So those numbers that are being outlined in black, they are the sorted part of the list. And as we sort the left side and then look at the next item in the list, putting in the correct place of our sorted left side, we're inserting, this is called the insertion sort, where each time in red I look at a new number, find where it goes in my left side already sorted portion, and then I go on to the next number, find its place, and as I find its place, notice I'm shifting the items in my sorted list. I'm shifting them over until I find a place for the new item. So visualizing this problem will help you understand the code. Looking at the 4, shifting the elements in my sorted portion until, oh, there's the spot for my 4. So a lot of shifting happening. Here we go through one more time. Look at the first element. Okay, it's sorted. One element by itself. Look at the next element. Okay, fit it in my sorted portion. Now I have a larger sorted portion. Look at the next element. Shift over until I find the right spot for the 3. Notice when it gets to the very beginning, we know that that's its spot. For the 1, same thing. I'm going to shift everything over until it's less than the next element in the list. So before even thinking about the code, you can draw, here's the concept of how I would do this sorting. And then you can start thinking about the code. Like, for example, I'm looking at shifting and swapping at the bottom there. Remember what shifting is. It's just assigning the element index to be the value next to it. And so it becomes the value to the right of it. And now 4, we're going to be doing some shifting over. We've already stored what's at position, each position as I go. Finally find the right position, and now there's the replacing. So shifting and replacing. As you draw the picture, then you can start thinking about, okay, let's, instead of writing the code right away, let's think through the code. And this is what they call the pseudo algorithm. This is presented in the book. They give you this pseudo algorithm. And it's written a little bit more like code, but at certain points, we don't write code. We just say, here's what we want to do. We move each location 1 slot down. And if you think through this, you'll see that it's doing what's illustrated here in this explanation of the insertion sort. Now, the thing about this problem is someone else has already solved it, and they're showing you how they did it. So this is an easy problem, except for the part about making the code go with what they conceptualize as a solution, and making your code follow the language of programming that you're using. So the pseudocode would work for any language. If you go to Wikipedia, they also give you a piece of code. I think someone wrote this with 3 lines of C code, and they show that on Wikipedia. But we're doing it with more lines so we understand what's happening. So going from looking through each element in the list, in the picture, we turn that into that outer loop of I'm looking for something that's out of order. I'm using that as going to be my index, first out of order. Notice it starts at the value 1 because when that first one is sorted, I'm always looking to the things to the right of it as I sort. So I'm looking at things to the right of the 0th element, and I'm going all the way to the end of my list as I increment this first out of order. So the outer loop basically is going through every element in my list. I'm going to be looking for every element. That means no matter how long my list is, or if my list is n elements long, I know I'm actually going through the loop n times. Okay, that's determining then how long this is going to take. And now, first thing I do is, if this element now is less than the one before it, if it's less than the one before it, then I know, I'm out of order, I need to swap. Notice first out of order, that's the one that's incrementing all the way to the end. This first out of order minus 1 means that's the one to the left side of it, okay? Which is the 0th element at the first time through the loop. So this is the test for, is something out of order? If it is out of order, I store where I found it into a temporary variable. And now I'm shifting all the elements one to the left, shifting the elements to the left of me over by 1 until I find an element that's less than me. That's what this is about. While location is greater than 0, while I haven't hit the beginning of my list, and I'm still finding numbers that are greater than me to my left. Because remember, to the left, location minus 1 means the element to the left. If it's still greater than the one I'm trying to find its place, then I keep going back until I find a spot for it. So again, that code goes with this picture. Looking for a spot for 3. Keep going to the left until I find something that's not less than 3. So going through the code, thinking through it, coming up with variable names. This author likes to use very long variable names. If you look at Wikipedia, they like to use I and J for variable names because it's a fairly small algorithm. So it's your choice as a programmer if you're going to use the long variable names. I use them in the code I gave to you just because it goes right with the book solution. And it helps as you're writing code to make the variable names long so you understand exactly what it's doing. You may find you like short variable names. That's your choice as a programmer. I do like them. It makes my code, I find it's actually, sometimes you get long variable names, but then it's hard to read the code and visualize what it's doing. And I always love the algebra where we use letters for variables. Okay, so finally, then we look at it another way. We're looking at, this is the book's explanation and its diagrams. There we have our unsorted list. And we're building, as we're building our algorithm, we're going to have a left side that's going to be partially sorted. And the next element I'm going to be looking for, a place for it. And so here is halfway through the algorithm. I'm going to have something sorted on the left and something new on the right. I'm still looking through. And the goal here is to move 23 to its spot in the sorted list. That's my visualized method is I have part of it sorted. I look at the next thing, find a spot for it. And right here we can see, oh, that 23 needs to go between 18 and 25. Well, we need to break that down into its steps by, first of all, making a copy of 23. So as I shift over these elements, I'm going to then be putting 23 in its correct spot. So I'm shifting over the elements and then replacing it once I get to the right spot. I need to put 23 in position 2. And so finally at the end, I'm doing the swap of 23 into its correct place. So another way to visualize the code. So again, solving the problem, visualize, here's the unsorted list. I'm going to be building up sorted portions. And the code that will take 23 and put it in its correct spot is the code that I have to write. So visualizing, stepping through, and of course, with this particular problem, reading how someone solved this problem, walking along, solving the problem yourself, now will help you solve other logical problems as well. Now I have given you this code. Let's go ahead and look at that and put it in our program to then do some testing and verify that we have the correct code, because I want to put testing code around this. Now let's go back now to Eclipse, or I'll show you this on UD Online. Let me bring up my web page. I'll have to stop the presentation. Go to UD Online and go to the assignment chapter 14. Make sure it's there. Now it didn't indent it right very nicely because when I copy and paste into the Moodle system, it wanted to left align everything. But we can easily fix that. So here's what we would do. This is over in chapter 14 exercise. You may have to refresh in case it wasn't showing up. I thought I had saved it. Go to chapter 14 exercise, and I'm going to, if you haven't yet started that, use that GitHub, you have to get that project from GitHub. But Monday we did this, but I haven't given you the insertion sort. So this part now I'm giving to you. I'm going to copy that, Control-C copy, and now go over to Eclipse. And I'll just do this from scratch just to show you how it all would work. I'll call this Insertion Sort 1, and I'll put it right in here as though I'm writing it for the first time. Make some white space for it. Oh, this is in the, since this is a sorting algorithm, I'm putting in the sorting.java program. I paste it, and because it's all left aligned, I want to correct my formatting. Remember how you can do this. You can select through the code, and Control-Shift-F to format it nicely. And now we have some nice indenting to go along with our code. And if you don't want to deal with all the extra white space, you could remove some extra lines. It's right in the assignment. Control-Shift-F will format selected code. So in the 14 chapter exercise, underneath activities, oh, where to paste it? Okay. Yeah, back in sorting.java as a separate method in sorting.java. I typically add my methods to the bottom of the existing ones. If you find you're using a lot of them, you will find it handy to alphabetize them.
So you don't put this under the insertion sort button?
No, I put this because this is an insertion sort. It's related to sorting an array. I want to put this in my sorting.java class. In the JFrame main, that's where we put things that are only for testing this specific program and the GUI related things. And since this insertion sort can be used for sorting any other data, I'm putting it in the sorting.java class. Yeah. This is in sorting.java outside of any other method, but inside the main class. Yeah. So outside any other method, and that's why at the end of every method, it's good to put, like, here's the end of the previous method. So you don't accidentally put your new code right inside some other method. It will not be happy. Sometimes it lets you do it, but then you realize it's broken later on when you actually try to use it. Now, I've given you comments here, and your job is to insert comments. So let's think through this code and insert comments before we get to the part where we're actually going to test this code. We want to be able to test this before we're done today. So let's think through this now. This is my outer loop. The comment here would be compare every element or I'll put here, process every element in my list. Now as I look through this code here, here's the test for, is something out of order? If the element I'm at is less than the element to my left, then I need to find a new place for it. Okay, so put a little comment here. Element to on the left is larger. Find a new spot for it. Actually, I'm finding a new spot for the first out of order. So first out of order, if it's less than the one to my left, I need to put this one over in the right spot. Because remember, it's not sorted if the one to my left is larger than the one to the right. See how first out of order minus 1 is the one on my left. So I'm saving this value in this temp variable. And remember, back in our picture, look at the picture in the explanation in the book. That's this thing right here. We're storing that value into temp. That's what we're doing right there. We're storing that position where I'm at into temp. That's what's happening right there. Now, I'm keeping track of my location as, what's this little loop doing? Let's see, I keep shifting. That's what this is doing, right? The list at my location is a list that is equal to what's to the left of it. So what's happening here? Shifting all elements to the right. See how I'm assigning what's here to what's on my left. So I'm actually shifting elements to the right.
Shouldn't that be the opposite then? From the minus 1 to...
Yeah, that's what's happening. From minus 1, it's being assigned into location. Location minus 1 is being assigned to location. So that means I'm putting what's on the left into what's on the right.
Right.
And this is confusing because the right to left equals, but remember, what's on the left is being put in the one with a higher value. So that's the sentence. That's what this loop is doing. And notice how long it's doing it. Either I'm at the beginning of my list, or I found something that's greater or that's less than mine. Let's see. Oh, that's a decrement.
Oh, that's minus 1?
Yeah.
Oh, that's it.
So I keep going to the left, shifting the elements over until I find my spot for where temp needs to go. Question? All right, let's do a little debugging here. We'll get this code working and compiling, and then we have to add the part to the regular method. We'll let you add the same method if it doesn't have the same variables, because that's allowed. And of course, with comments, you want to get your comments not to be misspelled, otherwise you don't look very smart. So try not to have too many misspellings in your comments, although it doesn't break your code. So I'm shifting elements to the right until items on left are smaller. So back to my picture, this part here is doing that part. Let's go back to the little picture here. Where'd the picture go? Let's go back to our picture here on this. This is the part where I'm shifting elements to the right until I find a spot. Either I'm at 0, that's what 1's going to do. Either I'm at the spot 0, that's the shifting to the right. Now I found a spot for that one. Here comes the 7. I'm shifting all the elements to the right until what's on my left, out of order -1, is smaller than me. So back to my code. And when you're doing code in this class, you cannot, I don't think it's possible to do too many comments. Think of that as a way you're keeping notes on why this code is working the way it's supposed to work. As you get more efficient at coding and you're professional, you will still have comments at the beginning of every function. Even the very expert programmers, they may not write as many comments, but you will still write comments for those that are reading your code what this particular method is doing. So I better put that here at the very start of this. And some people like to put the comments about the method right above it. Some put it right after the declaration of the method. I'm going to put it right here and just put sorts, I'll put purpose, sort the integer list. Notice it's not returning any value. It's taking the list and modifying it. And they call that, it's modified in place. I'm not making a new copy of it and sorting it. I am changing that as I go through this algorithm. So they call that in place sorting. I'm not making a copy of it first. Other algorithms, you may find they make a copy and then they return the new sorted list. These other comments, you can delete these because they're just telling you what you're supposed to be doing here. I'm going to leave this. Notice this is not the same as the one they give in the book. I'm only taking a list. I'm not taking the length because I find out as I was reading through the code, the only place that they actually use the length of the list is right here in this outer loop. And since I know since the list knows how long it is, why should I send it a second parameter? So I modified it thinking, all I need is the list. I know how long it is based on list.length. And I can do that same algorithm otherwise exactly as written in the book with the added comments. All right, now comes the part. We have the code. It should be working. Now we want to test the code. Let's save that and think about how are we going to test this code. And unfortunately, I've given you the GUI interface on this project. And I've given you a button right down here, Insertion Sort Test. So I just double click on Insertion Sort Test and let's write the code that's going to test this insertion sort. Yeah, so you open the design, and then once the design opens, just double click on the exercise 14.9 button. It will take you to the code. It'll be an empty function there that you then can start adding comments, and I'll walk through the plan. I've already thought as I was messing with this, I did a little verifying that system.nanotime will work, and it needs to be stored into a long variable, a variable type long. But that's going to come after I have a list. I need to actually have a list sorted. Well, I decided to make that a separate button just to, in case I want to sort other things. Back in my main design here, I want to have a list. And I can actually go look up in the code here. Towards the top here, I'm keeping track way at the top of a global variable called myList. Look at the very top of JFrame main. Now that list is not allocated, it's not initialized. So right now if I try to use myList, I'm going to get an error because the list has nothing in it. And I thought, well, I could generate numbers for myList, but I might want to use it in other places like testing other sorting algorithms. So I decided in this design, if I look at, I created a button called Create an Int List. This lets me create a list, then I can test that same list on multiple algorithms. So I decided to have a separate button just to create my list, and then I can test the sorting of it here. So let's click on this button, Create Int List, and now let's see how we would create a list. In this case, let's create a list of 1,000 numbers. Then I can sort that list of 1,000 numbers. Well, here's the code for creating a list of integers. And I'll enlarge that a little bit for you here. Here's the code for creating a list of integers. Put this under the Create an Int List button. Remember how to do that. In Design View, double-click the Create an Int List. And now I have the action to happen when I click that button. Did I give you this code? I don't remember if I gave you this code. Is that in there? Okay. Oh, good. I forgot that I'd given you that code. Well, let's make sure we understand what this code does. If you don't have it, you can type it in because it's not that many lines. It's right here. About 5 lines of code. First thing I do is say, I'm going to have 1,000 numbers. So I declare a list. No, I don't declare this. It's already a global variable, so I don't have to do int bracket myList. MyList is already a global variable. What I'm doing is saying, now I'm making room, allocating 1,000 integers for that variable. At this point, myList, my global variable myList, can now be processed. If I stop here, list is just full of zeros because by default it initializes all the values in this 1,000 long integer array to be 0. Instead of leaving the zeros in there though, I'm going to fill it with some random numbers.
So we're going by index, starting from index 0
all the way through the list.
Random value.
Yeah, and I'm putting a random number at every position. Here is how we generate random numbers. Very nice to know how to do this because as you use games or do calculations, you want things to generate some random data. At this point, I just want to generate a random integers. And remember what math.random does. It gives us a variable from 0 to 1. It gives us a double from 0 to 1. Yeah. So to get a number that goes up to 1,000, I multiply the random times 1,000. Okay? So that means it goes from 0 to 999.999, almost to 1,000. It doesn't quite equal 1,000. But if I want it then to go from 1 to 1,000, I can add 1 to that variable. And so that will give me a random number. This goes from 0 to 999.9. Add a 1 to it. And now what in the world is this thing doing? Have you seen that before? I'm not sure if you've seen this. It's called typecasting. It means convert, this is a double, take this double number that has decimal in it, and essentially throw away the decimal part of it and turn it into an integer. That's called typecasting. I'm casting or converting, having the compiler convert this into an integer, throwing away the decimal part. And that's because I have to do that because this is an array of integers. If I don't have that typecast in there, watch what error I'll get. It'll say, type mismatch, cannot convert from double to int. So that's why this is a double. I need to store the integer part of it into my list at position I.
So what's the difference between typecasting And parse input.
Parsing input essentially does the same thing, but it's actually doing two. It's converting the text into a number and then saying, okay, that number then gets put into a double or an integer. This is, I know I have a double here, so I don't have to do any parsing of it, but it's very similar to parsing. Or I know I have a double here that this function returns, but I want to store just the integer part of it. That's where the typecast comes in. Very common to do, especially when we're dealing with random numbers that I only want the integer part of it, that typecasting. And I want to show what's in my array, so I just display it into my text area sort output. And I'm only, rather than show all 1,000 of them and fill that text area up, I decided, if I see the first 50 random numbers, then I'm happy that it is working. So then I can save this with my comments. Let's run it just to see that it does generate some numbers. Here I get 50, and it looks like they are going from 0 to 1,000. Yeah, create the int list. That creates the my list. Now I have an array. Now this guy is ready to run because he sorts that my list. But before doing that, let's look again at that code that does the sorting. Brandon, were you able to get your... let's go back and look at that code now. Back in the sorting part of it, let's go down there to where that is. Right here. Nano time is what gives me my clock. Now, I don't have the code around here. I want to see that it got sorted. So I need to display the elements in my list. So since I've displayed it before, let's go ahead and just copy paste that code rather than rewriting it. I have the code up here where I've sorted or showed my first 50 elements. Let's just copy paste that. And back down to, where was I? I lost my, there it is. There's the insertion sort. Since I'm already displaying the list when I created it, I don't have to display it again. Let's just paste that code here. That one by one goes through my list. First of all, it prints out the first 50 elements and appends it. But this says after the sort is done. Oh, and I made a mistake here. I don't want to capture the time after I've done that. I want to capture the time before I display it. Don't do anything else before you capture the end time. I accidentally, we want the start and end to be the only thing that happens after the insertion sort. And now that we've captured the time, let's go ahead and display the time that it took. So here I'm displaying, yeah, the list did do the sorting. Let's append our measurement. So let's do another txt. Here's a little secret. If I do .txt, it shows me my available elements in my GUI. If I just type dot, and then I can do .append, and we'll put time taken, time to run, semicolon, and get rid of this. Time to run is concatenate that with, what is it, clock and minus clock start. What's that? Yeah. And I can get rid of that dot now that it gave me my helper.
I think I'm missing the remove, add, and whatever from that. I'm asking on the story J on the next file. I have the remove, add.
Oh, We can come back to that. So I wanted to get to this, and then we can go back and look at remove at. Okay, so because I'm taking up too much space here, I'm going to just append that to the end and then add the end line, just so it's readable on the screen. You don't have to add the new line here. I'm adding the \n. Now I should get the sorted list. Let's see if this runs now. First thing I have to do is create the list. I see I've got numbers there. Now let's sort that list. And it sure looks like it got sorted. And look at that. It's kind of interesting. You see I had multiple 7s. And oh, time to run 2842090. I'm guessing that's nanoseconds. That seems like a rather large number. I wasn't expecting that number to be so large. Microseconds, milliseconds. 2 milliseconds. I guess that's okay. 2.8 milliseconds. I didn't realize that clock was so accurate. Yeah, I was guessing they meant nano. I forgot to put a new line before that time to run. I want to see that on a new line. So there is my testing of that insertion sort. I got my clock start, ran the insertion sort with my list, got the clock end before I decided to then show that it looks like it actually did work. Now there's more things you could do with this. You could make it, let's just go make it a larger list and see how long it took. I have the case 2 milliseconds for 1,000 numbers. Let's go back to that, and instead of 1,000, let's make it 10,000. Where's that code where I made my list? There it is. New int 1,000. Let's make that. Let's go 100,000. 2.8 milliseconds before. Let's see how long it takes now. Oh, I have to end my previous versions here. Otherwise, I don't know what code is running.
Do you multiply it by 100,000?
I made it 100,000 long this time, and now let's see. I have to create the list. Still the numbers are only going from 1 to 1,000. But now sorting that, let's see how long it took. Uh-oh, it took a little longer there. That was about a second, 1.092 seconds. So fairly accurate clock there. And this is where you would compare one by one to one sort to another. In our case, we're not asked to compare insertion sort to some other sort. You can read all about that on Wikipedia. There's like 50 different sorting algorithms that smart people have devised over the years. And they've actually found that, I think the heap sort, figure which one's most efficient. This insertion sort is actually most efficient for any arrays up to about 50 elements long. After that, those other sort algorithms become faster. And it has to do with all that shifting and swapping. The less that you have to do, the faster your algorithm will be. Friday, we'll finish up this code. Try to see if you can do the remove at. If you need any help with anything, send me an email. I can give you help with the code.
This code available somewhere at GitHub?
Well, the start of it is that GitHub link I gave you in the assignment, the very start of it. And now I've given you this insertion sort code, but the finished one isn't yet available.
What we did today is recorded, right?
Yes, and I am stopping the recording right now, and it'll be uploaded this morning.